Example 3.1.10, a 30 MVA 11 kilovolt 60 Hz 3-phase 4-pole Y-connected synchronous generator has excess or synchronous reactance of 2 ohms per phase and a synchronous resistance of, or an armature resistance of 0 ohms. Determine the power angle when delivering rated power and voltage at a unity power factor and determine the maximum power output of the generator. So the givens here, if we just are writing what we've got down, we've got the 3-phase power of the generator is 30 MVA. The line-to-line voltage that it's rated to is 11 kV. It is 4-pole. Remember that, oh, I skipped one, 60 Hertz. F is equal to 60 Hertz. The symbol for poles is P, so capital P is equal to 4. XS equals 2 ohms. Armature resistance equal to 0 ohms. And we're going to say the power factor is equal to 1. We're asked to find power angle. Sorry, it took me a second to see that. Delta is the symbol for power angle at rated conditions. And we're asked to determine the maximum output power that this generator could possibly deliver before it loses synchronism, P max. So just to remind you what's going on, we have a generator. It's got some sort of excitation voltage that comes from its interaction of the rotor with the stator, and then we've got the synchronous reactance of the generator, which causes a voltage drop to its output terminals, VT, which is where the load is connected at. So we need to determine what the angle of EF is here. And once we do that, we can determine what the maximum power output of this generator is. So for a power factor equal to 1, we know that VT and IA are in phase. Right? And hopefully you recognize that IA is that current right there. So that brings up kind of an interesting point. The power factor equals to 1 is from the perspective of VT, not from the perspective of EF. So since this is what's observable at the output of the generators, we're considering the power factor being 1, meaning that VT and IA are in phase, not that EF and IA are in phase. So if these are my conditions I'm going to operate under, you probably should at this point be able to kind of draw your own phasor diagram, maybe not with numbers, but you'll know that VT points in that direction. That means IA is in phase with it. That means there's going to be a 90 degrees of voltage drop across XS. That's IA, JXS, synchronous reactance, and that means EF is going to look like that right there. So we can, for this power factor is equal to 1, we get the simplified equation that EF squared is going to be equal to VT squared plus IA JXS squared. And it's a triangle, so I mean the magnitudes of those sides, right? So to do this, we need to know what IA is, and we need to know what VT is. So the VT was given to us in the problem statement up here. We were told that we want to find the power angle when it's delivering rated power and voltage. So there's our rated voltage on a line-to-line basis. So to get it to VT, we just need to convert it to a phase quantity. So VT is going to be 11 kV over root 3, and that's going to be 6.351 kilovolts. I guess I should have written the magnitude of VT, but we're just looking for the length of this vector, really. Now we need to determine the armature current flowing out of the terminals of this generator, and I get that from the power. So IA is going to be equal to the S on a phase basis divided by the terminal voltage, and I need to take the complex conjugate of that, and so IA is going to be equal to the single phase power, which was 30 MVA. The power factor was 1, so we know that it's at an angle of 0 degrees. We divide that by 3. That gives us single phase power. Now we need to divide all that by the terminal voltage, 6.351 e to the third. Throw that in your calculator, take the complex conjugate of it, and you're going to get a current of 1,575 at angle 0 degrees amps as the armature current. As you should. Current should have an angle of 0 degrees since the power factor is 1. So good way to check. This voltage drop here, IAJXS, is going to be determined from 157.5 at an angle of 0 degrees times J, and the synchronous impedance was 2 ohms. So that's going to be, hold on one second. All right, I thought I had a math calculation error there. It's going to be 3150 at an angle of 90 degrees volts. And so that confirms that that's at a right angle to the voltage. That angle 90 right there does. So now I can write EF squared is going to be equal to VT, which is 6.351 e to the third, square that plus 3150 squared. And you're going to get a value of 7,089. Oh, sorry. I already took the square root of that value, so we'll just manipulate that by doing that. There we go. Now it's right. So 7,089 volts is the excitation voltage for this. So that still didn't give us delta, which is what we're after right here, right? We just calculated the magnitude of this right here. So how do we get to delta? Well, we can take this information, now that we know the length of the excitation voltage, we can just use the law of cosines there. So delta, let's see, we would say cosine of delta. Cosine is adjacent over hypotenuse, so that's equal to VT over EF. And so that gives us delta is equal to the arc cosine of 3150 over 7,089. Excuse me, not 3150. That's this voltage here. We need 6,351 kV. No, 6.351 kV. There we go. 6.351 divided by 7.089. That's correct. So we take the inverse cosine of that, we get 26.39 degrees is equal to delta, the power angle. The astute amongst you could recognize that we could have just done that with the tangent here. We could have taken inverse tangent to get that delta right there. That would have been fine too. I just wanted to show you again a calculation of the excitation voltage. So that gives us the power angle of the generator. And next what we want to know is Pmax. So there is a rule about generators is that delta can't go above 90 degrees. Delta has to be below 90 degrees, and so the Pmax occurs in a formula, and that formula was basically a manipulation of the output power formula, P out. We did some math and we found that if we take the magnitude of the terminal voltage and we multiply it by the magnitude of the excitation voltage, divide that quantity by the synchronous reactance, and then multiply by the sign, of the power angle, we get the output power. So we know that sine delta is when this whole thing is going to be maximum value is when sine of delta is 1. And so this here, when this is 1, this gives us the maximum power since sine delta varies between -1 and 1. That means this equation here maxes out when sine of delta is 1. And so we get Pmax. The maximum power that a generator can deliver is going to be equal to the absolute value of the terminal voltage times the absolute value of the field divided by x sub s. So that means we have 6351 times the value we calculated for EF, 7089, divided by 2. So that gives me 22.51 megawatts of output power. Now, you might say, this machine was rated to 30 MVA. Well, remember I calculated VT in EF here, and this was on a per phase basis. So that's a per phase output. So the actual max output power, Pmax 3-phase, is going to be equal to 3 times that. So 22.51 times 3 is going to give me 67.53 megawatts 3-phase for the absolute maximum output power before this generator loses synchronism.